Is it working for you? Yep, we had it. Hello? Is this working? Okay, so I'm gonna just let Alex know. Yep. Yeah. Yeah. Alrighty. You may do so as well, but you can say in the voice chat, Georgia, if you want. Oh shoot, I just said your name online. We can cut. We can cut. Okay. Okay. Enjoy. Oh man. Adios. Let's see. Let's get this set up. Well, to all my viewers out there, I love you so much. We're going to be doing the Calculus BC 2023 FRQs. It's going to be just a chill stream. We're going to maybe encounter some problems. We're actually going to encounter six problems, but I'm still getting set up just a bit. I have a pen here. My setup is pretty sketchy, as noted by my friend, but um, we enjoy talking to ourselves, so. We do have the first, um, we do have the first, problem open, but let me go ahead. Okay, let me just close this down. Um, and yeah, if we need that, this should work. Okay, we can do that. Yep. Okay, cool. Um, let's go back to. Oh wait, shoot. Does that ruin all my? Does that ruin my setup? Shoot, that might ruin my setup. Okay, so we will avoid going to Desmos as much as possible, but that's all right. We won't need it until we won't even need it for only one of the FRQs. So, um, I'm just gonna wait for a little bit to get some more people. Um, yeah. So, if my informal moderator could let me know when I probably have three viewers. I think we've got two more people coming. So and then I'll start around then. Hello. Resize tabs right now? Oh, shoot. You're right. I see what you mean. I think I see what you mean. I could do this. Resize it to the same size. Like this, you mean, right? My chat is kind of late. Actually, you could also be in touch with me through Discord if anything, uh, is necessary to know to me, in the moment. But yeah, this was an interesting exam. We had, and some interesting questions, like the realistic boiling of milk problem. But yeah, let's see. Hopefully, we'll get a few more people. Yep. Okay. I just gotta let another viewer know. Yep. Setup looks good. Okay. Thanks. Okay. Y para mis seguidores que hablan español, hoy vamos a solucionar las preguntas abiertas del examen de cálculo BC. Y este stream va a ser un poco chill y no va a ser mucho. Puede que hago errores, pero está bien. No, no, no quisiera ser perfecto, nada más quiero compartirles este momento y sí, nada más poder pasar este momento con ustedes. I did that to waste time. Oh, three watching. Okay, cool. I'm sure there's one more. Oh, shoot, yep. I gotta help out this other person. Let me see. I just discovered that I'm not sick, but allergies exist. They started existing earlier for other people, but allergies are something that's happening nowadays, so we have tissues just in case we need it. Yeah. Let me see. Can I? Oh, no, come on. I can't do that. Alrighty. Yeah, just to respond by voice to my chat members, we did forget the password, and it was to reset something. Yeah. I thought it was still like VVV something. And whoa, whoa, whoa. Don't say my name on the internet. This is a private space. I would never share my information on the internet, so I would appreciate if you respected my privacy. But yeah, full disclosure, my name is Corey. Okay, we should have about 4 viewers now, right? I think it's about a fair time to start. Yeah, if we do AP Stats senior year, we'll figure out what Alex meant. Alright, we've got our handy dandy pen, which has a little, I don't know what they call these things, a little padding on the end to write our things. Let's go ahead and see if we can write. Can we write without destroying our thing? We can write. Okay, so we're beginning our answer this way. Yep, that solves part A. But anyways, let's take a look. Let's begin officially. So this is problem one of the AP Calculus BC 2023 FRQ. And so I'll go ahead and read it. A customer at a gas station is pumping gasoline into a tank. The rate of flow of gasoline is modeled by a differentiable function f, where f of t is measured in gallons per second and t is measured in seconds since pumping began. Select values of f of t are given in the table, so we have f of t and t. So we're given a rate function for, in this case, gasoline. I wonder if there's any way I can make this larger, but it's all right. We're going to have to sacrifice that. No way. My admin ghosts are alive. Let's go ahead. So using correct units, interpret the meaning of the integral from 60 to 135 of f of t dt in the context of the problem. So also we need to use a right Riemann sum with three subintervals to approximate the value of of the said integral. So this is fairly easy. So let's go ahead and we know that this is a rate function. So when we take the integral of the rate function, we're going to get the accumulation or amount of change in whatever we're measuring, in this case, gallons. So that is going to be the meaning of the integral in this case. It's going to be the amount of gasoline that was pumped into the tank from time 60 seconds to 135 seconds after pumping began. But let's go ahead and tackle the Riemann sum. So right Riemann sum, we're going to use these values here. First, this one, and then that one. I'll go ahead and cancel those out. But let's go ahead and just start with our calculations. I have a calculator on my side as well, a scientific one, and let's just do this really quickly. This is easy. We know our first Riemann sum will consists of 30 times the value at f of 90, which is 0.15, plus our second rectangle, which has a width of 30 times 0.1, the value of f of 120, plus 15 times 0.05, because 15 is the difference between 120 and 135, and 0.05 is, thank you, Alex, that. Anyways, putting this into our calculator, I'm pretty sure it's 8.25, but it doesn't hurt to double check. 30 times 0.15 plus 30 times 0.1 plus 15 times 0.05. I did that wrong in my calculator. Sorry, let me do that again. Times 0.15 plus 30 times 0.1 plus 15 times 0.05. Yep, 8.25 is our answer. And if we're just going to write a quick, I don't want to answer all of the written stuff fully, but we're just going to give a brief sketch of what a full response would look like. So we're just going to say that from 60 to 135 f of t dt equals 0. I'm sorry, that's a terrible 5. Signifies that from time 60, to 135, 8.25 gallons have, I did that's better, were pumped. Because this solely signifies how much gas is pumped between time 60 and 135, not how much is in it at that time, at the end of 135 seconds. This is quite terrible handwriting. Hopefully we'll get a use of this 10 in this setup by the end of the stream. So pumped into the tank. Okay. So let's look at, sorry about that. You guys are welcome. I trust you guys with my life and everything apart from my life, also with my death. So once I inevitably die, you will be in charge of my funeral. So must there exist a value of c for c is less than 60 and c is greater than 60 and less than 120, such that f prime of c is equal to 0? Justify your answer. So we're trying to guarantee that a value for the derivative of f of t exists at a certain value. So, hey Ashley. So we know that we're going to be looking for mean value theorem, because that states that if a function is continuous and differentiable on an interval, there is guaranteed some point in that interval for which the derivative is equal to the tangent line, the slope of the tangent line. So let's go ahead and look at our function again. So we are given that it is a differentiable function, which also guarantees continuity. So let's go ahead and just write out the initial steps of the mean value theorem. So let's go ahead and find the slope of the tangent line from 60 to 120. So what we get is slope of tangent line, tangent equals 0.1, because that's the value 60, and also the value at 120 is that. Really, we don't need to write this out because in the end, it turns out this is equal to 0. So we know that there must exist a value c for c greater than 60 and less than 120, for which f prime of c equals 0. And we can prove that by saying since f of t, I'm going to abbreviate this, is continuous and differentiable, the MVP, not MVP, Uh, all of you guys out there are the MVP, but we're talking about the MVT, mean value theorem, guarantees a value between 60 and 120, for which the derivative, I could have just written this with the word of the question. Honestly, that is what I did on the exam, and I hope this is not being taken as an example for how to do FRQs. This is just a chill stream, for which the derivative equals the slope of the tangent of the tangent 0. So let's just go ahead and move on to part C. Oh my goodness, sorry guys. So this one is going to be calculator work, but let's go ahead and write our expression. The rate of flow of gasoline in gallons per second can also be modeled by g of t, which is this function, t over 500 times cosine of t over 120 squared. Using this model, we'll find the average rate of flow of gasoline over the time interval 0 to 150, and it does tell us to show our setup for our calculation, so we're just going to do that, and then I will basically plug the exact setup I have in my calculator. So let's just go ahead and do this. The average rate of flow of gasoline, so that's basically that's the average value of our function g of t over this interval, and so we know the average value of a function is going to be the integral, in this case from 0 to 150 of our function g of t dt over 150 times minus 0, which is just 150. And so I am just going to leave it at that and plug it into my calculator. Might take a quick second though, because I need to enter the function over 500, so just give me a quick second to do that. While we're waiting, just to check, my audio is okay and everything? From 0 to 150 of our function that we put in, dt. And this gives us, okay, cool, thanks. We're just gonna truncate 0.095997. We don't want to round up the nines. Why not? Why would we do that? So we can just leave that at that. So finally, the last part, part D, using the model G defined in part C, find the value of G prime of 140. Interpret the meaning of your answer in the context of this problem. So realistically, what you want to do on the exam is just put in that function, find its derivative at 140 using your calculator function. And I'm debating on whether I should just actually calculate the derivative. No, all we're going to do is we're just going to write calculator. Sorry guys, I know you were just desperately wanting me to actually solve the derivative of this mysterious function, but we are not feeling it today. We are just going to plug in g prime of 140, because I entered in as a function in my y equals section in my calculator, and we're just going to quickly use the derivative function on our calculator for that. At 140 equals negative 0.00491 approximately. And so, we don't have much space here, but let's go ahead and interpret the meaning of your answer in the context of this problem. So this is just the rate of change of the rate of flow of the gasoline. So let's just go ahead. Rate of flow of gasoline is decreasing by 0.00491 gallons per second squared. That's problem one. That wasn't too bad. I'm sure most of us got that. Let's go ahead and move on to part two then. Oh my goodness. Oh, we'll save. We'll save. Uh-oh. Is it? Oh, yeah, there we go. That works. Alrighty. So, we are given the second problem. Let's look. Sorry. Okay. So problem 2 states for t is greater than or equal to 0 and less than or equal to pi, a particle is moving along the curve shown so that its position at time t is x of t, comma, y of t, where x of t is not explicitly given and y of t equals 2 sine t. It is known that dx over dt equals e to the cosine of t. At time t equals 0, the particle is at position 1, comma 0. So this is particle motion problem. Let's go ahead and start with A. Find the acceleration vector of the particle at time t equals 1. Show this out for your calculations. So the acceleration vector will just, since we are given that this position, the particle's position is a position vector, all we need to do is just find the second derivative, because we know the first derivative of position is velocity, and the second derivative of position, or the first derivative of velocity, is acceleration. So let's go ahead and, so we're already given the first derivative of x of t, the position function for the x coordinate. So to find, we know our, so we're just going to find the second derivative by deriving dx over dt. So we can find d squared x over, oh my goodness, sorry about that, over dt squared. I don't know why I gave myself so little room for this problem, but equals, so this is going to be a chain rule. It's going to be e to the cosine of t times the derivative of cosine, which is times, negative sine of t. And for y of t, we just find the second derivative. The first derivative is easy. We'll just quickly get through that. It's equal to 2 cosine t, and then y double prime, I'll make that better, sorry, equals negative 2 sine t. So with this, we can construct our acceleration vector, and our acceleration vector in its general form will look something like this: negative sine t e to the cosine of t, comma, negative 2 sine t. And then we're just going to plug in these values on our calculator. We're going to plug in t equals 1. So let's go ahead and do that really quickly. And also, if you're in the chat and your name is your YouTube username, is it okay if I just say your name, because we all know each other here? So I'm specifically referring to one person. Plugging in negative sine of 1. Make sure you're in radian mode on the exam. But all of us have already taken, oh no, not all of us have taken the exam. Some few people here might take the exam later on, who I hope do. So for our x, we're given negative 1.444, etc. We're going to trunk it at 3 decimal points. And then negative 2 sine of 1. Bam, we're given negative 1.6829. Didn't need to go that far, but it's all right. That's our answer. That's our acceleration vector. Find the first time t at which the speed of the particle is 1.5. Show the work that leads to your answer. So this is going to require Desmos, because we need to obviously find a point graphically where the line y equals 1.5 and the speed function, which we'll define soon, intersect. So let's go ahead and find speed. Speed is since this is a vector, we know we have different magnitudes of speed going in the x direction and the y direction. So we know that the net speed is going to be the magnitude of the x and y velocities, which is given by the formula. I'll just go ahead and write this here. Speed equals, this is not its chemical formula, but we don't need that until organic chemistry. X d, oh yeah, dx over dt. This is written very poorly. Don't mind this. So yeah, don't worry about this at all. I'm so consistent. Squared is good. Move that. And if we want to write it out more fully, we can go ahead and just say it's e to the cosine square, e to the cosine t squared, because that is our dx over dt given by the problem, plus 2 cosine. We found that our y prime is that there. And so let's just go ahead and plug this function into Desmos. Let's grab our handy dandy Desmos, whatever this is. Square root of e to the, oh my goodness, e to the cosine. Oh, functions, there we go. This is not a fun menu, but we're going to use x by any means. I forgot, let me go ahead and, it's a bit interesting doing this on a touchscreen keyboard, but to cosine of x squared. Oh, I feel like I need to create some parentheses around that. There we go. And let's go ahead and write out 1.5. That's the value we're looking for. Oh, sorry. Y equals 1.5. And so the first time it equals this is 1.254. We see that because the next time, this is outside the range, but we're looking for the first time from what was it? From 0 to pi. So the first time is going to be just this one right here, 1.24. So let's go ahead and write that down. From calculator, t equals 1.254. I believe that was the value. Yep. Moving on. Oh my goodness, I'm sorry. Find the slope of the tangent line to the path of the particle at time t equals 1. So the slope of the tangent line will be equal to y minus y1. Oh, wait, let me just quickly check. Which value are we given? We're given at time equals 0, that equals 1. Oh, find the slope. Oh, sorry, I was going to find the entire formula for the tangent line, but no, we just need the slope. And the slope is going to be dx over dt over, oh my goodness. Also, this is wrong. I apologize. We started with the wrong variable. We can make this a y. dy over dt over dx over dt. And this is equal to, well, we're given dx over dt, and we already know dy over dt from our last one, so this is equal to 2 cosine of t divided by e to the cosine of t. Yep. And at time equals 1, we just plug into our calculator, which I'll do really quickly. 2 cosine of 1 divided by e to the cosine of 1 equals 0.6295. And find the x-coordinate of the position of the particle at time equals 1. So we're given the initial position at time t equals 0. It's at 1, 0. So we just need to find the x-coordinate so we can just track the progress of the x position through an integral. So we're given dx over dt, and we're given the initial position of 1. So we know that position, oh, that was not an A, position at t equals 1 is equal to 1 plus the integral from 0 to 1 of dx over dt. And you'd probably want to write this on the exam, what dx over dt is, but for our sakes, we don't need to. Let's just go ahead and pop that into our calculator, and from 0 to 1 of dx over dt, which is e to the cosine of t dx. And that gives me 3.34. So approximately pi. We can actually just write pi there. The College Board will accept that. There we go. And moving on, just for that's obviously a joke. It's 3.3415. Find the total distance traveled by the particle over the time interval. Let's just get through this. This is really simple. Well, simple if you learned it in class. The formula for total distance will be the integral, in this case from 0 to pi, of our speed. So let's just go ahead and set up that 0 to pi of our speed function, which, as we addressed earlier, is e to the cosine t squared plus what was it? 2 cosine of t squared. And let's go ahead, bring that, put a dt there, and pop it into our calculator. Let me just check. That is the same one as I had before. Yep. So we're just going to quickly pop this into our calculator. Real nice and easy. 0 to pi of square root of e to the cosine of x in this case, squared plus 2 cosine of x in this case. I have x as my variable. That, oh my goodness, accidentally put a plus sign at the end of my expression, equals 5.833. And by the way, if you guys find out that I make any errors all along the way, go ahead and let me know in the chat, because I am sure that it's definitely not out of my range to make a lot of errors. But this is just chill. We're gonna just work through it. That's the end of this problem, actually, so we can move on to the funny boiling milk problem. I believe that's next. Yep, that was problem 2. Let's go ahead and move on to problem 3. Save that. Yep, okay, so a bottle of milk is taken out of the refrigerator and placed in a pan of hot water to be warmed. The increasing function m models the temperature of milk t at time t, where m of t is measured in degrees Celsius and t is the number of minutes since the bottle was placed into the pan. M satisfies the differential equation dm over dt equals 1/4 times 40 minus m. At time t equals 0, the temperature of the milk is 5 degrees Celsius. It can be shown that m of t is less than 40 for all values of t. So we sped run that. That was a little bit long, and this one, we need to sketch the solution of the curve, so not the differential equation itself. Let's go and do this in a different color. We're going to do it in white, since this is milk. I'm just kidding. Let's do it in lavender, because why not? We like that color. So we know initially it's at 5 degrees, so the College Board gives us this point here to begin with. And really, we just follow the derivatives here. So we know it's just going to be increasing function by a lot, and then it slowly measures out until the derivative becomes 0 and it stays at the same value. I could execute that better to just show that. So let's show this. There we go. And then we're just at the same value. There we go. That's a solution curve. That is actually not dark enough, but it's good enough for our purposes. So part B says use the line tangent to the graph of m at t equals 0 to approximate m of 2, the temperature of the milk at time equals 2 minutes. So the line tangent to the graph of m at t equals 0 would just be, let's go ahead and switch back to black, y minus 5, or just to make it a little bit easier, y equals dm over dt, at 0, which is just 10, because we have dm over dt is 1/4 40 times m. So when we plug in m equals 0, we're just given 40 over 4, which is just 10. So that's our slope. So we have 10 times x minus 0, which is just x, plus 5. That's the initial y value. So let's go ahead and approximate that by just, oh, sorry, I should not be using x here. It should be t. And also, preferably we could put y as equal to m. let's go ahead and just, yeah, let's not, you can erase that actually. I'm sorry. This is going to be beautiful erasing. We're taking our time. This is a chill stream. There we go. Let's not erase that. So we're going to correct ourselves here and say that m equals 10t plus 5. That should be right. And then just plug in t equals 2. M of 2 equals 10 times 2 plus 5 equals 25. Bam. Yep, because like we said before, we have the initial condition that at time t equals 0, milk is at 5 degrees Celsius. Alrighty, write an expression for d, the second derivative of m in this case, in terms of m, and use it to determine whether the approximation from part B, which we just did, is an underestimate or an overestimate for the actual value of m2. So give a reason for our answer. So let's go ahead and write out dm over dt just for reference. Oh, I am sorry. Whenever I get near to touching the edge of the computer, it does that. dm over dt equals 1/4 40 minus m, and which is just equal to 10 minus 1/4 m. So when differentiating this, we'll have to use implicit differentiation since m is not our independent variable, it's our dependent variable, which is dependent on t. So equals, the derivative of the constant will be 0, so we are left with negative 1/4 dm over dt, which, as we established earlier, will just leave us with a total of negative 1 over 16, because we combined the two 1/4s together, 40 minus m. There we go. That's our expression. And so at m equals 2, we know that the second derivative is at, so I'll just go ahead and write at t equals 2. The second derivative is going to be let's see, just quick mental math. 40 minus 2 is equal to 38. Negative 38, which is negative 19 over 8. Negative 19 over 8. So what this tells us is that since the second derivative is negative, it's concave down. And so if we were to just go ahead and draw a funny graph, let's do green. This is an example of a concave down function, and let's draw. Our approximation from part B is a tangent line, so we basically did this. And as we can see here, that was not on even tangent to the graph, but yeah, as you can see, like pretend this is t of 0 and this is t of 2 here, we see that it's an overestimate. And we can simply say that because m of t is concave down at m of 2, that was inaccurate wording, sorry, at t equals 2, it's an overestimation. Okay, that is not meant to look like an A, but we tried our best. And this is the arguably more fun part. We're going to just solve the particular solution to the differential equation given the initial condition m of 0 equals 5, which is the initial condition given to us in the beginning of the problem. So let's just go ahead and quickly separate those variables. So by separation, dm over 40 minus m equals 1/4 dt. I'm not even going to bother writing, I'm just going to say integrate, and we get negative ln of the absolute value of 40 minus m equals 1/4 t dt. So let's go ahead and carry on this let's move the negative sign over, times both sides by -1, and raise it to the power of e to get rid of the, oh my goodness. Wow. Wow, Alex. So we are left, after we do this, raising to the power of e and getting rid of the -1 in the opposite order, which I said it, minus m equals negative, oh, I forgot the plus c, but why did I write dt? Oh my goodness. I am, wow, June, that's crazy. Plus c, we forgot our plus c here. Yeah, right, that was an error. But we know that we can rewrite this as e to the -1/4. Also, that negative should not be there. My apologies. This is what you do when you don't write out your work. Minus c. Really, when we say minus c, it's just going to be some form of c or another. So we can let's just go ahead and drag that down using exponent rules. C e to the -1/4 t. And just solving for m, we get 40m equals 40 minus c e to the -1/4 t. Yep, and plugging in our initial conditions, m of 0 equals 5, so we know that, let's drag this over here for our initial condition, 40 minus, and so we're going to plug in, no, m does not equal 0, it equals 5, sorry, but we know that t here is 0, so we know that e to the -1/4 t will be just 1. So 40 minus c equals 5 in this case, and so we can solve c equals 35. Then plugging that in, we get our particular solution, m equals 40 minus 35 e to the -1/4 t. That is our solution. Let's move on to, let me make that better, sorry, I kind of marked up over some of my work. Let's go ahead and move on to problem 4. I do not know of this Otto von Bismarck stream, but I guess I would say you guys should check it out. But you guys should stick on YouTube and move to Twitch and have both open at the same time. Okay, this one is our piecewise function. The function f is defined on closed intervals -2, risen to the power, oh my goodness. I just got a Discord notification from my silly moderators. Anyways, back to the question. The function f is defined on the closed intervals -2 to 8 and satisfies f of 2 equals 1. The graph of f prime of x, the graph of f prime, the derivative of f, consists of two line segments and a semicircle as shown in the figure. Does f have a relative maximum, a relative minimum, or neither at x equals 6? So to determine this, we need to look at the behaviors of both our derivative and our second derivative. We're given the graph of the derivative, and so we know that a relative minimum or a maximum will occur at a critical point where the first derivative is equal to 0, and that is the case as seen on the graph here. Let's go ahead and just circle that. That is our point. Our derivative is equal to 0, but however, we see by the tangent line right there that our second derivative is also equal to 0, indicating neither a relative minimum nor maximum, however, rather a inflection point. So since f double prime of 6 equals 0, neither min nor max, inflection point. This is a great explanation. This will get you full credit on the AP Calc FRQ if you explain just like this. No, it won't. So on what open intervals, if any, is the graph of f concave down? So remember, open intervals is asking for, give a reason for your answer. So when concave down, let's go ahead and get rid of, sorry, never mind, we're fine. Basically, concave down is equivalent to the second derivative being negative. So we see this happens very clearly from -2 to 0 because the slope is negative, and from 4 to 6 since the slope is negative. So let's just go ahead and those are our quick answers, easy. I'm just going to write the interval since we're on a move on. So from the interval from -2 to 0, 4 to 6. Okay. Find the value of limit as x goes to 2 of 6 times f of x minus 3x all over x squared minus 5x plus 6. Or show that it does not exist, justify your answer. So by direct substitution, we can show that this gives us the indeterminate form of 0 over 0, but let's go ahead and remind ourselves that f prime of 0, f of 2 equals 1. So, welcome, Tor. Welcome. We're glad to have you. Honestly, I feel like this could get boring to watch because we're just going through problems we already did, but we're gonna press through, and I guess what really matters is the Taylor stuff in problem 6. But I'm sure you might pick up on stuff along the way if there is. So f of 2 equals 1, as I said. So plugging in by direct substitution, if we just plugged in x equals 2, we're given 6 times 1. So ds, or I say direct substitution, 6 times 1 minus 3 times 2 over 2 squared minus 10 plus 6. That's just all. And this is equal to 0 over 0. So since we have an indeterminate form, we can use L'Hopital's rule. We love L'Hopital, L'Hospital, as it's very correctly spelled. With a little, I forgot what that was called. Yeah, Tor, don't forget to check out Otto von Bismarck's stream at the same time. So let's go ahead. This L'Hopital states that for a limit given in the indeterminate form by direct substitution, we can just that the limit is equal to the derivative of the numerator over the derivative of the denominator. So we just quickly find out that 6, the derivative of the numerator, minus 3. Yeah, I can't believe my moderators are conspiring against me. That's the derivative of the top over the derivative of the bottom, 2x minus 5. Now let's see if we can plug in. So f prime of 2 is equal to 0. So we get 0 minus 3. Plugging in 2 on the bottom, we get 4 minus 5. This equals negative 3 over negative 1, or just 3. That is our limit. Justify our answer. Our justification is L'Hospital. L'Hospital. That's a very famous hospital cross. I think that proves our point there. Find the absolute minimum of f on the closed interval -2 to 8. So how I did this, and how many of you did, I am sure, is our relative extrema will occur at critical points, which are at I'll use blue this time, are at point 1, because the derivative 0, 2, the derivative 0, and 6. 6 we already ruled is not going to be a minimum, so we know that we don't need to worry about that. And we don't need to worry about negative in 1 either, since it's concave down. We know that at this point, at this critical point, it will have a relative maxima. We're only looking for relative minima, so that leaves the only critical point we need to take into consideration here is f of 2. So we're going to need to do some integration here, which I am not looking forward to, but let's just do a table here really quickly of x and f of x. We need to consider our bounds, -2, so we know that f of 2 equals 1. So our integral will be 1. To find f of -2, the integral from it'll be -2 to 2 of f of x dx, or this is equal to 1 minus, by integral properties, to -2 f of x dt. So let's just go ahead and dt. Oh my goodness, we're having aneurysm. D asterisk. So let's go ahead and just calculate our area from -2 to -2, from -2 to 2 rather. So we have a little triangle here that has a value of 2 times 1 over 2, or just 1. This has the same area here from -1 to 0. So we know those will cancel out, and we are just left with this right here, this little triangle here to get us to 2, which is equal to 2 times 2 over 2, which is just equal to 2. So we are left with, well, negative 2 rather, since it's under the x-axis. So we're left with 1 minus negative 2 equals 3. We already know f of 2 is just equal to 1. So far we can rule out this value of negative 2, and intuitively 8 will also be able to rule out since we only have positive increments. We have this positive triangle here. We have in the area under this semicircle here, as we're only increasing our value from f of 2. So, but just let's go ahead and solve this. We know the semicircle has a radius of 2, and we need to find the area under it in the circle here. And this triangle here has an area of 2 times 2 over 2. So this is just 1 plus the integral from 2 to 8 of f of x dx equals 1 plus 2 from that triangle plus the area of this rectangle here is 2 times 4, 8, so 8 minus, so 1/2, our area of our semicircle will be 1/2 pi r squared, r is 2, so 2 pi. Did I do that right? Am I tripping? I think I'm tripping. Am I tripping? 8, yeah, 8 minus 1/2 pi r squared, r is 2, so that'd be just 2 pi, yeah. And either way, we don't know the exact value, but we know that this is going to be 11 minus 2 pi, and which is obviously less than 1, making this the answer. Just kidding. 2 is our answer. It still has the lowest value, and the absolute min on negative 2 to, on the closed interval of negative 2 to 8 is 1. Bam, that is problem 4 done. We're almost to the end, folks. Thank you for bearing with me. I'm sure you're having a great time. Let's save that. Beautiful drawings. Okay, this was a fun integral problem. We're given two functions, f of x and g of x, for which on the area defined, f of x is greater than g of x. It is known that g of x is 12 over 3 plus x for x greater than 0, and the twice differentiable function f, which is not explicitly given, satisfies f of 3 equals 2, and the integral from 0 to 3 of f of x dx equals 10. So let's get into this. Find the area of the shaded region enclosed by the graphs of f and g. So we know that the area between this will essentially be the area of g of x minus the area in red of f of x. That was beautifully drawn, but intuitively it makes sense, so we can just go ahead and write our integral expression, which is integral from 0 to 3, because those are our bounds, of g of x, 12 over 3 plus x. Let's go ahead and put this all in parentheses, minus f of x here, all times d of x, and this is, we can just split up those integrals. We know the integral from 0 to 3, as given here, of f of x is equal to 10, so we are just left with integral from 0 to 3 of 12 over 3 plus x times dx minus 10. And to simplify this further, let's go ahead and drag it down here. Our antiderivative will be 12 ln of the absolute value of 3 plus x, evaluated from 3 to 0, minus 10, equals, so just plugging in using the fundamental theorem of calculus, we get 12 times ln of 6 times 12 minus 12 times ln of 3, which let's just put this all into mental math. This will be using log properties. What is that equivalent sign? I am sorry. This is ugly. This is atrocious. We are going to fix that. Ln of 3, the absolute value of 3, which is just 3, because we did, my bad, I cannot math 2, because 6 divided by 3 using log properties is 2 minus 10. That is our answer. Evaluate the improper integral, the integral of 0 to infinity of g of x squared, or show that it diverges. Let's get started. So let's go ahead and we know that g of x is equal to 12 over 3 plus x, or let's say x plus 3. Let's go ahead and plug in our laptop really quickly. Just so that it doesn't die midstream. There we go, that's better. There we go. Yep, screen just got brighter. Sorry about that. So let's go ahead and write our integral. The integral from 0 to infinity of g of x. I don't know why I wrote two parentheses there. That was not necessary. Alright. But anyways, so this is equal to, let's go ahead and just put our limit in there immediately. Limit as b goes to infinity, because you cannot evaluate an integral with infinity in bounds since that's not a number. Integral from 0 to b of 144, because that's 12 squared, and x plus 3 squared dx. Let's go ahead and get our antiderivative. So the antiderivative will carry over the limit. B goes to infinity. And x of 3 is just a compound function whose derivative is equal to 1, so we don't need to worry about it. All we need to know is that we're going to use the inverse power rule to say that we get the limit of negative, because as you'll see here, x plus 3, because that's just x plus 3 to the negative 1, and so when you do the derivative of that, it'll cancel out the negative sign here to create our original function here. I don't know, I'm going to leave this explanation very limited because it's just simple power rule, inverse of it rather. I did take the PCs at the power station, thank you, Gino. Evaluated from 0 to b, and this is equal to limit as b goes to infinity of negative 144 over b plus 3 minus, or since we're minusing a negative, just plus 144 over 0 plus 3. And this evaluates, since we're taking b's, it goes to infinity, the denominator will go to infinity, and we'll get an infinitesimally small number, or just 0, which is, so it's just equal to 0 plus 144 over 3, or we can just scribble that out. It's not real. 144 over 3. That is our answer. And finally, our last part of this one is let h be the function defined by h of x equals x times f prime of x. Find the value of the integral from 0 to 3 of h of x dx. So let's go ahead and rewrite our integral using the definition provided of h of x times f prime of x dx. So this looks like integration by parts. Let's go ahead and set u equal to x and v equal to f of x in this case, or dv is equal to f prime of x. But either way, I'm not actually going to use these variables. I'm just doing that for viewer convenience. So we're given, using the formula, the integral of u dv is equal to uv minus the integral of v du. So we have our uv here, x times f of x, minus the integral of v. Oh, I'm sorry, I forgot to include this. Since this is a definite integral, we do need to evaluate this from 0 to 3. And also, minus the integral from 0 to 3 of v du, which in this case is just, the du will just be 1, derivative of x, so f of x. And we're already given this integral, as always, conveniently. The integral, I'm talking about this integral right here. So that is equal to 10, as noted up there. So we can set this equal to 3 times f of 3 minus 0 minus 10. That's our integral. The 0 comes from evaluating f of x at 0, because the plugging in 0 as x will just yield 0. And this is equal to What is f of 3? What do we do here? Oh, it's equal to 2. We are given that right here. So f of 3, 3 times f of 3 equals, 3 times f of 3 is equal to 3 times 2, or 6. I was right, right? Ooh, sorry. Yep. So 6, that was a beautiful 6, minus 10 equals negative 4. That is our answer. That is the integral from 0 to 3 of h of x. On delay, let's move on to part 6. The long waited for Taylor polynomials. So the question states the function f has derivatives of all orders for all real numbers. It is known that f of 0 equals 2, f prime of 0 equals 3, f double prime of x equals negative x to the x squared. Negative f of x squared, and f triple prime of x equals negative 2x times f prime of x squared. So our first task is to find f to the fourth derivative of x, with respect to x. Write the fourth degree Taylor polynomial for f about x equals 0. Show the work that leads to your answer. So let's just go ahead and remind ourselves of what a Taylor polynomial, TP, we're going to call that TP equals the infinite sum, starting from x equals 0, n equals 0, holy crap, folks, we're going to get this right, f to the nth derivative of a is where we're centering it at, and we're centering it at 0, so a will equal 0 in this case, times over n factorial times x minus a to the n, and since a is 0, it's just x to the n in this case, but that's the general formula just to remind ourselves. So the fourth degree Taylor polynomial will go up to we'll go up to the fourth derivative, sorry. Am I paused on your stream? I cannot see my face moving anymore. Is everything good? Can someone in the chat confirm that we're all good? Because I currently am frozen, on my screen at least. Uh-oh, technical problems. Let's go ahead and see. Oh, yeah, something happened. Huh? Interesting. So you can still hear me on YouTube. That should be right. I have no idea what just happened to my Discord here. Let's go ahead and pull up chat again. Let me text a moderator. Our Wi-Fi is still good. Discord is just being the one that's funny here. Right, so you guys can still hear me. Okay, cool. Yeah, I have left Discord. It's fine. Let's go ahead and expand our chat in that case. Can I? Oh, reconnection successful. There we go. I have no idea what's going on. But let us press on. I've said the problem twice now, so I think you guys get it. So let's go ahead and find f prime, f to the fourth derivative. Not f to the fourth derivative, sorry, the fourth derivative of f. So we know that this is just d over dx of f triple prime